In this video, we focus on one of the key topics of lecture W5B, which is frequency conversion. Frequency conversion, as opposed to modulation that converts a baseband signal into a passband signal, or demodulation, which converts a passband signal into a baseband signal. Frequency conversion converts a passband signal into another passband signal at a different carrier frequency. So the initial carrier frequency we call omega c, and the target or final carrier frequency we call omega c prime. And a frequency conversion, it's a linear process. That means it's a linear translation of the spectrum. There is no change in the bandwidth of the signal, only its center frequency location. The strategy for frequency conversion means or is based on mixing or multiplying the signal to be converted by a properly tuned mixing carrier at a frequency that we call omega sub mix, which is the frequency of the mixer, and then apply some filtering operation. So it's very similar to DSP modulation and DSP demodulation, only that in this case we are in general converting a signal that is passband into another signal that is passband. We have two types of frequency conversion. We have up conversion, that is when the target frequency omega c prime is larger than the original frequency omega c, and down conversion if the new target omega c prime is lower than the original frequency omega c. And both up conversion and down conversion can be achieved via two different strategies. One is super heterodyning. That means that the mixer frequency, the omega of the multiplier local carrier, is the sum of the original carrier frequency and the target carrier frequency. Sub-heterodyning, on the other hand, means that the frequency of the mixer is the magnitude or the absolute value of the difference between the origin and the target frequency. And here we need to use a magnitude because we can have a positive or negative sign depending on whether we're doing up conversion or down conversion. So let's start with an example of down conversion. In this down conversion example, we start with a message that's modulated in DSB, as you can see here, at a frequency omega c, and we end up with a message that is also modulated in DSB, but at a frequency omega c prime, where omega c prime will be lower than omega c. In this case, we're going to use a mixing frequency that is omega c plus or minus omega c prime, depending on whether we're using a super heterodyning strategy or a sub-heterodyning strategy. But in both cases, the result is a DSB signal at the new frequency omega c prime. In the case of super heterodyning, so in this case, the mixer frequency is omega c plus omega c prime. And therefore we can write the signal here at x of t as m of t multiply cosine omega ct. This is the input signal, and then multiply by the mixing frequency omega c plus omega c prime t. If you use this trigonometric identity and work these terms, you can show that the final result is 0.5 multiplied by m of t multiplied by cosine at omega c prime, and then cosine at 2 omega c plus omega c prime. We call this the desired term, and this is going to be a byproduct or a high frequency term. If we use the strategy of sub-heterodyning, so in this case, the omega mix will be omega c, that's the original frequency, minus the target frequency. You can write the signal x of t in this way, cosine omega c minus omega c prime. And then again, using this trigonometric identity, you can show that the result of that is 0.5 m of t cosine omega c prime t, that's a desired term, plus the byproduct or the high frequency component. And in the spectral picture of these, you will see that the desired component falls exactly at the desired frequency, omega c prime, and then there's a high frequency term that needs to be filtered out, For the subheterodyning option, that product is at 2 omega c minus omega c prime, and for the superhet the option, the term is at 2 omega c plus omega c prime. Those terms are filtered out by this bandpass filter, which you can see here the response. It's a bandpass filter centered at omega c prime, which gets rid of these byproducts. But let's take a more detailed look of this process of frequency conversion applied as a up converter example, in which we are doing DSB modulation as a two-stage process. So we're going to have first a low frequency DSB modulation. This is what you need to do when you have a circuit that doesn't support operation at very high frequencies. So you modulate at a frequency that is more not so high, let's say in the hundreds of the kilohertz, and then you convert this frequency to a much higher frequency for final transmission. So in this case, you can see a DSB modulator. This is the message. This is the first carrier, omega CT, and this is the DSB signal. And you can see the spectrum of the DSB signal centered as expected at this lower frequency, omega C. But now comes the up conversion process. For the up conversion process, we're going to multiply by this omega mix carrier, or carrier at omega mix, where omega mix, in this case, we're going to assume that it's super heterodyning, so we're going to use the plus sign here. Omega mix will be omega C prime plus omega C. This is the location of omega mix, which is higher than omega C prime. That's our target frequency. And when you do the multiplication here, you get a translation of the spectrum. You can see that the whole spectrum here, the DSB spectrum, is translated to omega mix, giving rise to these two components, one at omega C prime and this high frequency subproduct. And then the second version of this spectrum appears at negative omega mix. That's negative omega C prime minus omega C. That's giving rise again to these two terms. Now these two terms contain the desired up-converted DSB signal, but we need to get rid of this one. So for that, we're going to need a filter. That's what this filter does. The bandpass filter centered at omega C prime will get rid of the high frequency component and leave you with a DSB signal modulated at omega C prime. Let us look now at the subhet version. In the subhet version, we use the minus sign of the omega mix equation here. That means that the omega mix frequency is below omega C prime, is around here. And again, you will see the translation of the full spectrum of the original DSB spectrum, both to omega mix and to minus omega mix, giving rise to these four components. Now, because we're doing subhet up conversion, the byproduct is not going to be a high frequency byproduct such as this one. It's going to be a low frequency byproduct, which still needs to be eliminated through the bandpass filter. So again, the bandpass filter omega C prime will remove this low frequency component, and that will end up producing this DSB signal at the new target frequency, and we call the combination of the mixer and the bandpass filter, which made it possible to convert the carrier to a higher frequency, we call it the up converter, and the result of that will be a very high frequency DSB signal. Let's look at a final example now with respect to the application on a satellite transponder that's doing down conversion. Now, down conversion in a satellite transponder is necessary because the transponder essentially picks up a signal coming from the Earth, so it's an uplink signal going at a higher frequency of 6 gigahertz if you are working, let's say, in the C-band. So that signal at 6 gigahertz needs to be converted for retransmission on a different antenna that's aimed at a different geographic area, and the transmission must operate, the downlink transmission must operate at a lower frequency, let's say 4 gigahertz. So here you see both transponders. The signal coming from this antenna at 6 gigahertz, it's converted down to 4 gigahertz for retransmission to the Earth, and then the signal coming up on this antenna at 6 gigahertz it's down converted to 4 gigahertz for retransmission to the Earth on the downlink at 4 gigahertz. Here we're using the sub-heterodyning alternative, and the reason for that is we want to avoid very high frequencies in the satellite, because those high frequency components tend to consume more power, and power is very limited in the satellite. Also it gives rise to more complicated circuits. So that's why we use, in those circumstances, we use sub-heterodyning. So in this case, the omega mix we're going to use for down conversion would be omega c minus omega c prime, omega c being the 6 gigahertz signal coming up, and omega c prime being the 4 gigahertz signal coming down. That means that the omega mix will be 2 gigahertz. And you can see here the 2 gigahertz frequency. So what's going to happen now is this spectrum at 6 gigahertz will be translated linearly to 2 gigahertz, giving rise to two components. One of them at 2 plus 6, 8 gigahertz, and the other one at 2 minus 6, that's negative 4 gigahertz. That's for these component centered at 2 gigahertz. There will be a component centered at negative 2 gigahertz. You can see it here, and that gives rise to two components here signaled in blue, where this component is negative 2 gigahertz plus 6 gigahertz, that gives you 4 gigahertz, and then negative 2 gigahertz minus 6 gigahertz, that gives you negative 8 gigahertz. So that's what's coming out of this multiplier. So if the signal is coming out this way, you get a filter at 6 gigahertz, and then the mixer, and then comes a second filter. The second filter is at the omega c target frequency, omega c prime target frequency of 4 gigahertz, and that's the filter that's going to eliminate, in this case, a high frequency component, allowing for the generation of the signal of 4 gigahertz. So you can see here that the effect of the whole circuit has been to simply translate the spectrum from linearly, without any modifications. It's a translation from the 6 gigahertz to the 4 gigahertz downlink frequency, and that's what the purpose of the down conversion in this case is.